I haven't said anything yet. So we learned from Mladen's first lecture that one of the most fundamental objects in mathematics is the circle. And I'd like to add one more to the list, and that's the interval. And I'll spend my 4 lectures talking about these 2 objects mostly. So from the point of view of homotopy theory, they're not terribly interesting, but mostly I'll be interested in discussing groups which act on them continuously and with higher regularity also. Okay, so what we're going to be interested in particular is groups of homeomorphisms, homeo plus of M, where here M is one of these 2. And this is the group of orientation preserving homeomorphisms. And so for the first lecture, I'd like to talk about the continuous theory, which is to say, when I only assume continuity of homeomorphisms and no higher level of regularity, no differentiability or anything. And there's a rather pretty picture that has been developed over many decades of understanding at least countable groups which sit inside of these larger continuous groups. And so before I dive into this, I have to make an algebraic excursion into the theory of orderable groups. So a group G is, in general, I'll take left orderable. One can define an analogous theory of right orderable groups, and the theories have the exact same amount of richness. So if there exists a total order relation less than on G, which is somehow compatible with the group structure of G, so which is left invariant. So that is to say, for all triples, say A, B, and C, in the group, we have that A is less than or equal to B if and only if C times A is less than or equal to C times B. And so this order relation less than is called bi-invariant. If it is also right invariant, so that is to say, the same relation, the same equivalence holds, except we multiply C on the right instead of on the left. So that's just terminology. And for reference later, I'll just give immediately the definition of what a cyclically orderable group is. So G is cyclically orderable if there exists a function called omega from G cubed to the set consisting of 0 and plus minus 1, which is, well, first it's again left invariant, meaning that omega of A, B, C is equal to omega of GA, GB, GC for all A, B, C, and G in the group. And it's cyclically invariant. Which is to say, omega of A, B, C is equal to omega of B, C, A. And it's anti-symmetric. Which is to say that if you look at omega of A, B, C, this is equal to minus omega of B, A, C. And it has this transitivity property, which means that omega of A, B, C is equal to omega of A, C, D equal to 1 implies that omega of A, B, D is also equal to 1. And the last condition is that it has to be total. So that is to say, if A, B, and C are distinct, then omega of A, B, C is non-zero. So let's discuss these definitions a little bit. So the orderability of a group is somehow not very difficult to pick apart. Just means that you're placing all the elements of your group on the real line in a way that when you multiply on the left by a group element, then you preserve the order in which you place them there. And the cyclic orderability of the group is more or less the same thing, except you're placing the elements of the group on the circle now. And so on the circle you don't have an order anymore, but you can talk about triples of points being positively and negatively oriented. And so what this cyclic order is, this function omega picks out an orientation of all triples. And it's saying that, well, if you put all your elements on the circle and you multiply on the left, then this won't change the orientation of any triples. And so that's what left invariance means, and cyclic invariance means that if you look at if you read a triple in the same cyclic order, then you get the same orientation. And the anti-symmetric axiom says that if you have a triple and you fix one of the elements and flip the other two, then you get the opposite orientation. So these two you could really combine into an action by the symmetric group on 3 letters, and then you just get if you apply a permutation to the elements A, B, and C, then the result is that you multiply by the signature of that permutation. And then transitivity is saying, well, how do 4 elements fit together? So how do you, if you understand if you understand enough orientations of triples among 4 elements, then you can deduce the orientation of the 4th triple. And this is something called a co-cycle relation, but I'm not going to get into that. And this is just saying that this orientation is not choice of orientations is non-degenerate. Okay. So, as I said, that the history of orderability, especially linear orderability of groups, has a long and rich history. So some important names in the theory of linearly orderable groups include Kokorin and Kopitov. Also Fuchs. So this is the theory here was developed in the 1940s through 1960s mostly. And the interest here was primarily algebraic. So a particular motivating problem was the following. So in group theory, one thing that one can do is you can build an integral group ring. Okay, and so this is you look at the group, okay, as an abstract set of basis vectors. Okay, and you take the free abelian group on the elements of G, and then elements of the group ring are finite integral multiples of elements of the group, and you can add them together formally, and you can multiply them using the group law of the underlying group, with the coefficients commuting with the group elements. And now this module now acquires the structure of a ring, and one can ask about the algebraic properties of this ring. And so there's this conjecture called it's called the zero divisor conjecture, sometimes Kaplansky's conjecture. So which says that if G is a torsion-free group, then the integral group ring has no zero divisors. And in general, this conjecture is open, but here's a very informative exercise that's not very difficult. Which says, so if G is left orderable, then G satisfies Kaplansky's conjecture. So the theory of linearly ordered groups was also to a large degree expounded by the work of Akbar Remtula, Roberta Boromura, And, well, there are many other names. These are sort of the main contributors. And again, this was all from a primarily algebraic interest. And so that's one view of orderable groups. And then there's a second perspective which one can take on orderable groups, which is the one that we're going to concentrate on in these two lectures. There's a dynamical perspective. Which is through the study of subgroups of homeo plus of I and homeo plus of S1 and the relationship between these two. And I'll state now a particular theorem which I'll prove in a few minutes. So through the following dictionary between these sort of dynamical, these sort of abstract groups of homeomorphisms of manifolds and purely algebraic properties of groups. So a countable group is left orderable if and only if let's name this group, sorry, G. If and only if G can be realized as a subgroup of homeo plus of I, and similarly a countable group G is cyclically orderable if and only if G is a subgroup of homeo plus of S1. So the list of names that's led to the development of this theory is quite long. I'll name just a few. One can write Derwin and Navas and Gis, Monod, Whitty. It's a long list, and there are many very interesting open problems and research directions here. So this is the perspective to which we'll return in just a moment. And just for completeness, I'd like to mention one more, much more recent perspective from which orderability has attracted interest. And there's a sort of a topology geometry perspective. And this is due to the work of Boyer, Gordon, and Watson. And so what they formulated is something called the L space conjecture. And so what they, in particular, what they're interested in here is, well, you have a 3-manifold M3, and you want and so the L-space conjecture, I won't state it precisely. It's a relationship between the Heegard floor homology of M, which if you've never heard of that, that's okay. And the orderability of pi 1 of M. This is really one name I should not neglect to write here, which is Thurston. But no. Okay, so these are sort of the reasons people have been interested in orderability. And as I said, we're going to concentrate on the dynamical perspective. And so let's first maybe give a proof of this theorem, and then we talk about some examples, some straightforward and some not so straightforward. So I'm just going to give a proof for, or a sketch, mostly sketch a proof of the first part. Linear orderability gives rise to actions by homeomorphisms in the interval. Left orderability and homeo plus of I should say countable subgroups. Okay, so let's first make a certain simplification. So first I want to use some sort of algebraic properties of the target space. So I'm going to replace I by the real line. So if you have the group of homeomorph. So if you have an element F, which is an orientation preserving homeomorphism of the real line, then F extends to the 2-point compactification of R, which is to say R union plus minus infinity, which is homeomorphic to the interval just by, since F is preserving the orientation of R, you just send infinity to plus infinity and minus infinity to minus infinity. And similarly, so if F is an orientation preserving homeomorphism of the interval, then F is naturally an element then of homeo plus of the open interval 0, 1, which is exactly equal to homeo plus of R, because the open interval 0, 1 and R are homeomorphic to each other. So, in particular, it suffices to characterize left orderable groups as exactly countable subgroups of orientation preserving homeomorphisms of R. So let's suppose that G is inside of homeo plus of R, no countability assumed, then we claim is that G admits a left invariant order. So one way to do this is we take Q. I mean, Q could be replaced here by any dense subset of R, but it's important that it be a countable subset. Okay? And we just number it arbitrarily. It doesn't have to be numbered in an order-preserving way or anything. So here Q is A1, A2, and so on. Okay, so it's some countable list. So we set G to be less than H if, well, the only way that G can be less than H is that G and H have to be different elements of G, okay, of big G. And so therefore, they have to differ as homeomorphisms of the real line. And so if they are different homeomorphisms of the real line, then they have to differ on a dense subset, at least at one point of a dense subset of R, because otherwise continuity would force them to be equal. So we look at if we look at min I such that G of AI is different from H of AI satisfies G of AI is less than H of AI. So you look at the first index where they differ, and you define G to be less than H if G moves AI less to the right than H does. And this is an easy thing to check, is that this defines a total left invariant order. Okay, so that says that if you look at subgroups of homeo plus of R or homeo plus I always admit left invariant orders.
Here you don't need the countability of the group, right?
No, I didn't use anything about the count.
You only need the countable then subset of that.
Yes. So I'm going to need countability for the other direction. Yes. That's absolutely right. So now suppose G is countable and equipped with this left invariant order less than. Okay. Then, so write G is G0, G1, G2, so it's some countable list of elements. Again, this list is completely arbitrary. And so I'm going to define a function t from G to the real line as follows. it's going to be defined inductively. So T of G0 is just going to be 0. And suppose T of G0 all the way to T of Gi have been defined. So to make this a little bit clearer, so here's the real line, okay? And here's T of G0. So these are, these aren't homeomorphisms yet or anything. This is just a function from G to the real line. So I'm associating to every element of G just some real number. So T of G0 is just 0. Maybe here's T of G1. Maybe here's T of G2. T of G3 maybe is here, and then so on. So I've defined T on on the first I elements of G, and now I need to define it on the I plus first one. So ideally, T would preserve the order because that's what I'm interested in using in some essential way. So what I can say is suppose that Gi plus 1 is greater than the max of G0 to Gi and or respectively less than the minimum. So it's either bigger than or less than everything, all the elements that I've considered so far. Then what I can do is then I set T of Gi plus 1 to be equal to this maximum with T applied plus 1, or in the second case, I send it to the minimum. That's a perfectly reasonable thing to do. So now if you imagine that, for example, if these were the integers, if G were just consisting of the integers, and now it's just naming them one at a time, so 0, 1, minus 1, 2, minus 2, 3, minus 3, then I would, this way of defining T would just send the integers to the real numbers, which we think of as the integers. And of course, these conditions may not be satisfied. It's possible that Gi plus 1 lies between two elements which I've already considered. So, then suppose that that Gi plus 1 lies between Gn and Gm, for here n and m less than or equal to I, and let's say that there don't exist any elements S or any indices S and T such that Gn is less than Gs is less than Gi plus 1. So that Gn and Gm are exactly the predecessor and the successor of Gi in this order on this finite set. Then set T of Gi plus 1 to just be the average of T of Gn and Gm. Okay. So what have I done? So this gives an order-preserving function t from g to r. Okay. And there are two things that one has to check, which I'll leave as exercises. So the first thing is to check that, well, maybe three things to check. So note that, the first one is too easy, so I'll just say note that G acts on T of G faithfully. So, namely, you take G times T of H, well, just take this to T of GH. And this action is order preserving. So what this does is, now we've defined an action of G on a certain subset of R. Okay. So then we want to actually build an action of G on R. So check that this action of G on T of G extends continuously to an action of G on the closure of T of G. So the closure of T of G is generally going to look like one of two things. It's either going to be a discrete subset, so it looks a lot like Z, or it may look like a Cantor set, or there's one more possibility that it may be dense inside of R. And so in these three cases, you get this action of G on a closed subset of R. Okay? And so in the first of those cases, you get essentially a translation action on Z as a subset of R. In the third of those cases, you've already defined an action of G on R, and so you've finished the proof of the theorem. And in the third case, you have this sort of complicated Cantor subset of the real line, but its complement is a union of intervals. And so what you can do is, well, you can, if you have two different open intervals and they have two different lengths, and you can define a homeomorphism from one to the other just by scaling by the appropriate lengths. Okay? And so what you need to check then is that the action of G on the closure, T of G, closure, extends continuously to R. And that proves the theorem once one checks that. Okay. So now let's, with that sort of very general background, let me talk about some actual examples of ordered groups and how all this fits together in the real world. So the integers themselves are the simplest ordered group. So you can view the integers as a subgroup of R with the additive structure. And the ordered structure on R is inherited by Z, and it's left invariant. More generally, you can look at any subgroup of R with its additive structure. Now there are many more examples, so let's think of some which are not abelian. So let's consider, for example, finitely generated torsion-free nilpotent groups. This is a very important class of examples in order theory, and they'll come up later when we talk about regularity, because their regularity properties are very interesting. So the best way to illustrate this is probably with an example. So the example that I'll look at is what's called the Heisenberg group. And so this is the simplest non-abelian torsion-free nilpotent group. It has the following presentation. You can write X, Y, and Z as generators, and the commutator subgroup, or the commutator of X and Y is just Z, and Z commutes with both X and Y. So it's already kind of somewhat unclear just from first principles how one might find an order on this group, but there are many, and let me give a way of analyzing or building orders on H, which generalizes to more flexible constructions. So the Heisenberg group has a natural quotient, namely Z direct sum Z, and that's given simply by setting this element Z to be the identity. This is equivalently the abelianization map. Okay. Z is central, so you can quotient out by the subgroup generated by it. And what you're left over with is a group generated by X and Y. The commutator of X and Y is the identity, and then these two relations become trivial. Now, I claim that one can build order or left invariant orders on H out of left invariant orders on Z direct sum Z and on Z. So we already know that Z has a left invariant order, and there are exactly two of them. There's the usual order where you set the positive integers to be positive and the negative integers to be negative, and you can also flip that around if you wish. But how can one explicitly find a left invariant order on z direct some z, well, one can deduce it from this more generally statement. So for example, one can embed z direct some z inside of the real line with its additive structure by just sending one generator to, say, the element 1, and the other generator to any non-rational real number. For example, the square root of 2. Okay, so then 1 and the square root of 2 together, they generate a subgroup of R, which is isomorphic to z direct some z. It sort of doesn't look like z direct some z because it's dense inside of R, but that's what it is algebraically. And in general, here's a somewhat, I think, better way of understanding all the possible orderings one can put on z direct some z. So you can draw the Euclidean plane like this, and then z direct some z becomes just the integer lattice. So okay. And so one thing that you can do then is you draw a line through the origin. Okay. And now what you've done is you've cut the plane into two halves. Now, so if this line has irrational slope, then it won't meet any of the integer points except 0. Okay. So 0 is always this neutral element. It's less than any positive element and greater than any negative element. And so in the case where this line has irrational slope, then you just pick one of the sides and you say these will be the positive elements and everything below will be the negative elements, and that gives rise to a left invariant order one can check. Okay. And if you were bad at choosing the slope and it ended up being rational, okay, then you can still do the same thing. Is that you can say the things above this line, which whatever above means, it's your choice, are positive. Everything below is negative. But then you have some integer points lying on the line, and so you just choose a half of this line, and you just say that this half of the line is going to be positive as well. So then everything on this side is going to be positive. Everything on this side is going to be negative. So that was a digression, but the point is that this group has a lot of left invariant orderings. Okay. So now, let's say that I have an element in H.
Are they all?
Beg your pardon?
You produce a lot of ordering.
Yeah, so that is actually all of them. Yeah. Yeah, so that's a fun exercise. So every left invariant order on, in fact, this isn't even, you don't even need to assume two-dimensional anything. It's on z to the n comes from this, I'll call this the half space construction. Okay. So let's say you have elements G and H in H, and we have fixed orders less than sub z2 on this group and less than sub z on this group. And let's say I wanted to compare G and H. Okay. So the first thing I can do is I can apply this homomorphism phi and look at the image of G and H in Z direct sum Z. So if say phi of G is less than phi of H in Z2, then G will be less than H in the Heisenberg group. But of course, this homomorphism phi isn't injective. Okay, so for many elements inside of H, you can't make a meaningful comparison inside of Z direct sum Z, even though they're not the same element inside of H. But what does it mean for them to have the same image inside of Z direct sum Z? Well, it means that they differ by an element of the kernel. So what then I can do is I can look at G inverse H now, which sits inside of Z, the kernel of this map. And we say that, so if phi of G is equal to phi of H, oops, and G inverse of H is greater than 0 in Z, then G is also less than H. And that defines a left invariant order on H, so you can check that. So in general, one can build a lot of different ordered groups. So for example, so here's a general fact, which and the proof is an exercise. So if you have an exact sequence of groups like this, so this is a surjective homomorphism from G to H, and the kernel is exactly equal to K. And if H and K are both left orderable, then G is left orderable. Okay. So back to these examples. So finitely generated torsion-free nilpotent groups. And there's a generalization of this fact and of this one that says, in fact, you can take what are called residually torsion-free nilpotent groups, which are finitely generated. So what this means is that G is, I'll write RTFN, residually torsion-free nilpotent, if for all non-identity elements G, there exists a torsion-free nilpotent group N and a homomorphism phi from G to N such that G is not in the kernel of phi. So that means that the variety of residually torsion-free nilpotent groups detects non-triviality in the particular group under discussion. So I'll give you some examples of groups which are residually torsion-free nilpotent, which are not nilpotent themselves. And for all of these, this is a nice organizational tool, but it's possibly not the best way to see that these groups are left orderable. And that includes free groups and surface groups, that is to say, fundamental groups of closed surfaces. And these things called right-angled Artin groups, which will come up later. Also, pure braid groups, if you know what those are. If not, that's okay. Pure braid groups. Okay, so in the last few minutes, let me just say a few more non-examples. So probably the easiest source of counterexamples is, so remember at the very beginning I said that there's this Kaplansky conjecture about zero divisors in the integral group ring. And so as you sort of would expect, that if the group has torsion in it, then the zero divisor conjecture would be false for such a group, and that's indeed true. And so such a group shouldn't be left orderable in particular. That's true. So torsion is the main source, one of the main sources of counterexamples, so of non-examples of ordered groups. So if you have a finite order element, then you can just check directly using the left invariance of the order relation. So say 1, or the identity, has to be less than that element, or maybe it's inverse depending on what the order is, and then you can check directly that you quickly arrive at a counterexample. So check that a finite cyclic group is not left orderable. But returning again to Kaplansky's conjecture, it's not true that every torsion-free group is left orderable. There are, in fact, long laundry lists of conditions you can put on groups and still require them to be not left orderable. For example, there's examples of Remtula, who I mentioned earlier, who said that there exist finitely generated metabelian torsion-free non-left orderable groups. So this means that that the commutator subgroup of G is abelian. And in general, so if you're given some group which you don't know very much about, it may be very difficult to decide if it's left orderable or not. And there are, let me just say a few things about cyclically orderable groups. So examples of those include all left orderable groups. So the way that you can build a cyclic order on a left orderable group is, well, the one-point compactification of R is just the circle. So remember you have to define this orientation cocycle, this function omega, and you just take one of the points to always be infinity for that, and you can check that all the axioms are satisfied. From a dynamical point of view, well, the group acts on the circle fixing infinity. That's just the same as an action on the real line. And there are many more cyclically orderable groups than there are left orderable groups, but the theory is a lot more complicated. So, a finite cyclically orderable group is cyclic. So in particular, you can't have non-abelian finite groups acting by orientation preserving homeomorphisms of the circle. And so I think in the beginning of the next hour I'll have some discussion of mapping class groups, but I won't say very much about that right now. And the last thing I'll say is this sort of combination result here. So this is an extension combination theorem. And something like that also holds for cyclically orderable groups. So if you have an exact sequence of groups like this, the naive guess would be that if this is cyclically orderable and this is cyclically orderable, then that should be cyclically orderable, but that's not true. So if this is cyclically orderable and this is just left orderable, then this implies that G is cyclically orderable. And the only place that I know that this is written down in literature is a paper of Beck and Samperton. So I think this is a good place to stop.